In this video, we're going to talk about the orthogonal group. And there is an orthogonal group for every bilinear form. So in this video, we're going to talk about what a bilinear form is, and then define the orthogonal group of the bilinear form. So to motivate this, we recall that we have the dot product. So the dot product say of x and y, which is x transpose y. So this is defined to be x1, y1 plus dot 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 plus x and yn. This is the dot product on Rn. And it satisfies certain properties. So one of them is it's symmetric, meaning that the dot product of x and y is equal to the dot product of y and x. Another property is it's positive definite. Meaning that whenever x is not equal to the zero vector, the dot product of x with itself is positive. And in this video, we'll look at analogs of the dot product. These are the bilinear forms. But before we get to bilinear forms, let's explain how we can define the typical orthogonal group in terms of the dot product. So the orthogonal group O(n) of R is the group of matrices that preserve the dot product. Okay, what does it mean to preserve the dot product? It means that for all x and y, so for all x and y in Rn, so it's the group of matrices Q that preserve the dot product. So if Q is an orthogonal group, if Q preserves the dot product, it means for all x and y in Rn, the dot product of Qx and Qy is equal to the dot product of x and y. Well, let's think about what that means. So the dot product of Qx and Qy is Qx transpose times Qy, right? And then this is x transpose Qy. Now on the right, the dot product of x and y is x transpose y. So in other words, we need, for all x and y in Rn, x transpose Qy equals x transpose y. And one can show that this is true if and only if Q transpose Q, so this matrix, is the identity. And this is the familiar definition of an orthogonal matrix, right? A matrix is orthogonal if Q transpose Q is the identity. Or alternatively, if Q is invertible and Q transpose is equal to its Q inverse. Equal to Q inverse. Okay. So this orthogonal group is the group that preserves the dot product. But more generally, there's an orthogonal group for any what's called a non-degenerate symmetric bilinear form. So now I'm going to explain what a bilinear form is. It's a generalization of the dot product. So I'll take V to be a finite dimensional vector space over R. So here I'm not choosing a basis. So here we could think of V as Rn once you choose a basis for V. But here I haven't chosen a basis for V. So when you have such a vector space, a bilinear form on V is a map from V cross V into R that is linear in each variable. Okay, what does that mean? I'll write it out like this. So RV1 W, well, yeah, I don't know how to read this. Anyway, the bilinear form is written like this. So it's this it's like a dot product, except it takes two vectors in V and it spits out a real number. So it needs to satisfy these properties. This is a linearity condition. So these two conditions basically just tell you that you can pull scalars out, right? And then the other aspect of the linearity is that it distributes over sums. So it's going to be like that. So you have these properties for all V1, V2, W1, W2 in V, and all real numbers R. One example, so there are lots of bilinear forms, and it's easy to construct them. So suppose that A is, let A be an n by n matrix. Then we define this mapping to be X transpose A, Y. Then one can check that this is a bilinear form. Okay, pretty standard check from the definitions, just using the property of matrix multiplication. And in particular, when you take A to be the identity, you just get the dot product. Right? It's just X transpose Y. So this is a generalization of the dot product. Okay. Another definition is a bilinear form is symmetric if for all V and W in V, I don't know how to phrase this if I don't say the dot product, the bilinear form of V and W is equal to the form of W and V for all V and W in V. So that's the definition of symmetric. And then there's an alternative definition, or there's another definition, skew symmetric. If for all V and W in V, it's pretty much the same except with a minus sign. Okay, and another definition, a bilinear form is non-degenerate. If for all V not equal to 0, there is a V prime in V such that the form of V and V prime is not 0. Okay, so most of the interesting bilinear forms we're going to look at are going to be non-degenerate. So just like we have the orthogonal group when you have the dot product, right? The group of matrices that preserve dot product. So here we have Rn, right? But when we're talking about the dot product. But when we're talking about bilinear forms, we have just a vector space without a fixed basis. So we have to talk about linear mappings, right? Linear transformations from V into V instead of matrices. So the definition that we're going to give is the definition of an automorphism. An automorphism of a bilinear form on V is an invertible linear transformation, say T, that preserves the form. Okay, what does it mean to preserve the form? In the sense that the form of Tx and Ty is equal to the form of x and y for all x and y in V. So these automorphisms form a group under composition, and the group is written as aught of aught of this form. Right, so when V is equal to Rn and the bilinear form is the dot product, then we just get so when V is equal to Rn and this is the dot product, the automorphism of the form is just what we called O n of R. And in general, when the form is non-degenerate and symmetric, the automorphism group of the form is called the orthogonal group of the form. And it's written O of V if the form is known, right? It's the orthogonal of the vector space if we think of the vector space as automatically being given a symmetric non-degenerate bilinear form. Okay, so that's what the orthogonal group is.